Okay, so welcome to the second guest lecture on basics of graph theory. So today I'm covering trees. So we will be starting from where we left from the last time. And so I will just first introduce you to cut vertices and cut edges. We will need these things for defining for proving some theorems about trees. So a cut edge is an edge whose deletion increases the number of connected components. So a graph, so let's first go with the definition. So we write G minus E or G minus M for the subgraph of G obtained by deleting the edge E or set of edges M. So let's first see an example. So this is a graph, a standard, and this is a connected graph. So if you see this dotted red line, this is a cut edge. Why? Because when you cut it, you will get a graph which is disconnected, which has more than one components. So just see the definition again. So a cut edge is an edge whose deletion increases the number of connected components. So this is one component, but when you cut it, when you remove this thing from your graph, you get two components. So this is a cut edge. Is this clear? Say yes or no in the chat and then I'll proceed. Okay, I think it is clear. And now we come to the next definition, which is cut vertex. A cut vertex is a vertex whose deletion increases the number of connected components. So it's just the same definition, nearly the same definition. The only thing that is changing is now we are removing the vertices instead of edges. So we write G minus V or G minus S for the subgraph obtained by G, obtained by deleting vertex V or set of vertices S. And again, the same example, this graph is connected, and now we cut this. Now this we show that this is a cut vertex. Why this is a cut vertex? When you remove this is the resulting subgraph that you get. It now has three connected components. So this is one component, this is another component, and this is the another component. This is the third component. So again, see the definition. A cut vertex is a vertex whose deletion increases the number of connected components. So initially it had one. When you delete it, the resulting graph is this. It has three connected components. So this is a cut vertex. Okay. Now there's a very fundamental theorem about cut edge. And this also gives you a way to check whether an edge is a cut edge or not in a graph. You can use this to form an algorithm out of this. So edge is a cut edge if and only if it belongs to no cycle. So see in this, so let's see in this example, there are no cycles in this graph anyways, and also like this edge does not belong to a cycle. So okay, let's just go to this example and like let's change this example for a bit. Let's say if we add another edge here, then in this new graph, this will not be the cut edge. This 2, 5 is not a cut edge because when you remove the 2, 5, it is still connected. So that is the thing. Now this edge is belonging to a cycle. So now this is not a cut edge. So that's the intuition, and we'll prove this. So, okay. So first of all, I will assume that the graph is connected. And you can assume that without loss of generality. Why you can assume that? Because if you remember in the last lecture, I showed that a graph has many connected components. A graph can be written as decomposition of many connected components, and an edge must lie in one of the connected components. And you can just focus on that connected component. So because of that, we can just assume that our graph is connected. The proof will be the same, even if you don't assume, because your edge must lie in a connected component, and then you're just working with that connected component. So first we'll show that, first we'll assume that edge E is the cut edge, and we want to show that it belongs to a cycle in G. So keep in mind, we have assumed that G is connected. And now, just remember the definition of connectedness. So for any two vertices in U and V, you must have a path connecting them in G. So, oh, somebody's joining. Okay. So if we show that if UV remains connected in G minus E, so once you remove E, So I'm proving this by contradiction. I'm assuming that it belongs to a cycle, and then I'll show that why it is a contradiction. So now we assume G is connected, and we assume that this HE belongs to the cycle. So if we show that UV remains connected in G minus E, that means that this is not a cut edge, and we are done. So then we get a contradiction, right? Because we're taking any two vertices in G minus E, and we are showing that they're connected with the path. So that means G minus E, the number of connected components didn't increase, and that means that E is not a cut edge. So, okay, I'll just write here, we're proving by contradiction. Okay, so now we have to show that UV remains connected to complete this proof. So there are two cases for any path in G. Either that path so like we assume that the path is P connecting UV in G because G is connected. So there are two cases, whether that E is lying inside that path or E is not lying inside that path. So when E is not lying inside that path remains unaffected even in G minus E because you're not removing E from this path. So UV remains connected in G minus E. So you're safe. So like the graph is still connected if this case happens. Now we have to show that if E is in this path P, the graph is still connected. So how we are doing that? So we assume that E lies in a cycle, right? That is our assumption. We initially assumed that E is in a cycle. So we say that cycle to be C, right? Like, so it's already written here. So let me just point it out. So we have assumed that E is in a cycle, and this is the path P, and we are saying that E belongs to this path P. So when you cut this, when you cut this E, right, you still have a cycle connecting this edges of. You still have a cycle containing X and Y, and from that cycle you can still complete this path. So you can still make a path from U to V, and that path is this. You can still make a path from U to V so this is like P dash. So this P dash connects UV in G minus E. So, and you do this for all UV. So your graph is still connected. So then you get a contradiction. So is there any doubt here? Is this part clear for the proof? Just write yes or no, and then I'll proceed. Or otherwise, I'll just do the other way around, and then I'll repeat the whole argument so that you understand everything. Okay, so now we have to show the reverse implication. The reverse implication is if it belongs to no cycle, then we have to show that it is a cut edge, right? So okay. So we are saying that if G minus E is connected, then E is in a cycle, then we'll show that E is not a cut edge, and the proof is like same. So, oh no, there's something, I'm missing something here. So, okay. Okay. Oh no, this is the same proof. I'm sorry. Um, need to cut cut this proof out there completely. Okay. So now the reverse thing is we have to show that. Okay. So we showed this direction that if E is a cut edge, then it belongs to no cycle. Now we have to show if it belongs to no cycle, then it is if E belongs to no cycle, then it is a cut edge. Okay, so we can yeah, okay. So we can say that assume E is not a cut edge. So what does that give us? So like, so when G minus E is connected, so suppose the ends of E and so suppose this is G and this is E. When you remove E, okay, let's write something like this. X, Y, and this is E. So there must be some path from and when you remove E, X and so there must be some path. So this is U, suppose this is U and this is V. There must be some path connecting U and V somehow. Because if there is no path connecting U and V, then G minus E is not connected. It is getting you're getting two different connected components. So using this path, you have to construct a cycle. So like, so because this is also connected, this part is also connected. And when you remove this E, when you remove this E, it is also connected. So then you must have something here and you must have something here. And now you just see E was here. So you get a cycle. So I wanted to leave this as an exercise for you to formalize the above intuition. Okay. So what are the okay, now I'll just show now I'll just briefly go through all the steps of the proof so that it becomes clear to you. So an edge is a cut edge if and only if it belongs to no cycle. First we show that it is a cut edge. First we assume that it is a cut edge and we show it belongs to no cycle. So we proved this by contradiction. We assume that it belongs to a cycle and then we showed then it is not a cut edge. So we use this cycle to create a path. And the second, we assume that if it belongs to no cycle, then so we have to show if it belongs to a no cycle, if it belongs to no cycle, then it is a cut edge. So we assume again that it is not a cut edge. If it is not a cut edge, then again we constructed a cycle and we got a contradiction. And I just leave the next part for you to do it at your own because it's the same idea. Just you have to construct the cycle. So this completes the proof. So as an example, like if we have this graph like this, so none of these edges of the graph, none of these edges are cut edges. Because if you remove any of them, then you're still getting a connected graph. So I'm sorry. But if you remove suppose this edge, then you can get a cut edge because this edge is not lying in a cut in a cycle. So this is a way to check whether a edge is a cut edge or not. Okay. So is this clear? Just say yes or no in the chat so that I can proceed, or if it is not clear, then you can ask. Hmm. Is the definition of cut edge clear? Yeah. I assume it is clear. So then I'll proceed with the trees. So I'll just give you a brief review of the trees that we did last time, and we'll start proving some theorems that you will require for your course. So a connected acyclic graph is a tree, like I defined it last time also. So you need two things: a graph should be connected and it should be acyclic. Then it is a tree. We define leaf to be a vertex of degree 1. So in this graph, in this graph, this okay, this is not a tree because this is acyclic. This contains a cycle, so this is not a tree, but this is a tree. And these are leaves. These are degree 1 things. It has only one edge containing to them. And a spanning, and now I'll define something new, which is spanning graph, spanning subgraph, and spanning tree. So a spanning subgraph of, oh, sorry. A spanning subgraph of G is a subgraph with vertex at V. So any subgraph with the same vertex at V is a spanning subgraph. A spanning tree is nothing but a spanning subgraph, which is a tree. So any tree which covers all the vertices of the graph is a spanning tree. So some example. So this is a graph. Let's say this is a graph G. And so now this H is a spanning subgraph. Why? This is a subgraph. First of all, this is a subgraph. This H is a subgraph of G because it contains all the vertices. Remember, the definition says subgraph, not the induced subgraph. So it is a subgraph because it contains all the vertices. And this is a spanning tree. T is a spanning tree. So I just remove this edge. Now this is not a cycle anymore. So this is a spanning tree. Again, just reminding you that these are leaves, degree 1. This is not a leaf. It has degree 2. Okay. So now I'll come to another theorem. But before I go with this theorem, is there any question that you might want to ask with this definition? Is this definition of spanning tree clear? Spanning subgraph or spanning tree? Um, okay, I assume this is clear. Then we'll have another theorem, which is this. So we say that every tree with at least two vertices has at least two leaves, and deleting a leaf will give you a tree which produce with n minus 1 leaves. So if you have n vertices in the tree, deleting a leaf gives us a tree with n minus 1 leaves. So the intuition is like this. So if you have a tree like this, or and if you remove any vertex, then the remaining tree is n with one vertex less. So the intuition is very straightforward. So okay, so first, so like there are two parts that we need to prove here. First, we need to show that every tree with at least two vertices has at least two leaves. So okay, for that we assume let the graph G has n vertices, which n is greater than or equals to 2. So a graph is acyclic, so we can find a maximal path with respect to inclusion. A maximal path with respect to inclusion is like it is the longest path. It is not contained in any other path. Because it is acyclic, you can do that. You cannot repeat things. So like you can have like a one long path. And because your graph is acyclic and it has more than two vertices, you can always do that. And we just take the endpoints of this path. So endpoints of this path, any longest path, endpoints of this must have degree 1. Because if they don't have a degree 1, so you can extend that path. But we are assuming that this is maximal path. So you start with a path. This is the longest path, suppose. So the endpoints should have degree 1. Okay, so that covers this part of the proof, that every tree with at least two vertices has at least two leaves. Now we come to the second part, which is deleting a leaf from n vertex tree produces a tree with n minus 1 leaves. The intuition is very clear, but we still need to do a formal proof for that. So what we need to show that we start with a graph G and we delete the vertex V. So we get a graph G prime. G prime is what? G minus V. And we want to show that G prime is a tree of size n minus 1. Well, that is the number of vertices in this G prime is n minus 1. So this is so let's say this is our entire graph G. Like we are denoting this as G prime. So we are deleting this vertex V, right? And degree of V is 1. So it is only connect, so there's only one edge joining. So because these, so you're removing that edge. So when you're removing an edge, you cannot create new cycles. So you cannot create new cycles in G prime. So G is assumed to be acyclic and connected, right? And since this vertex has degree 1 only, that implies that G prime is also acyclic and connected. Remember, this is important. You can only say that because degree of V is 1. So removing this vertex V with that edge E does not add new cycle to G prime. So G prime stays acyclic. And G prime also stays connected because you have not removed anything from G prime. You have not removed any edge from G prime. So that shows that G prime is acyclic and connected with n minus 1 vertices. So I already showed you the intuition. We have a tree. I'm just saying removing a vertex, removing a leaf from a tree still gives you a tree. That is what the idea is. And this is the proof for that. So why this lemma is important? You will see that we use this lemma again and again in the proofs and constructions and algorithms. In your algorithm course, you will use this. So like intuition is that it gives you a way to construct trees from the smaller trees. So suppose you have tree of vertex of number of vertices in a tree is 2. You can just add another vertex to a leaf and it is still a tree. And you can just keep on doing that. So it gives you a way to construct trees from smaller trees, and it also gives you a way to construct smaller trees from the bigger tree. You just remove leaves, and then you get a smaller tree. So this will be helpful when we do inductive proofs over trees. And you need this when you're working with algorithms and you want to prove that your algorithm is correct or not. And sometimes you want to prove whether your algorithm is terminating or not over a tree. You need these kinds of arguments. So this is a very, very useful lemma for you. Okay, so I will take a pause here and let me know if this is clear or not. Just say yes or no, or if you have any question, just ask. Okay, I assume it is clear. Okay, so now now I will start with a brief review of what we did last time. So last time I gave you some equivalences between the trees, right? So if G is a graph with vertices V and E, edges E with n vertices, we say a graph G is connected and has no cycles, that is acyclic. This is tree, right? So this is equivalent to when a graph G is connected and has n minus 1 edges. When G is connected and n minus 1 edges, G has n minus 1 edges and acyclic. And for any two vertices U and V, G has exactly one path. So it's like saying if you have a tree, so all of the vertices are connected. It has n minus 1, so suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices. So we count the number of edges 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges. So it is n minus 1 edges. And if you choose any two U and V, there's only one way to go from U to V. This is the intuition for all that. So you can always draw an example and work with that example. So this is what we proved last time. And I also gave you some exercises when we proved the equivalences. Keep that in mind. So I can either say tree is something that is connected and acyclic, or I can say any graph that is connected and n minus 1 edges is a tree, or I can say any graph that is acyclic or n minus 1 edges is a tree. Or if in a graph G, if for any two vertices U and V, if we have exactly one path, then it should be acyclic and connected. So these all are equivalent, and I can use any of these things as a definition of tree. Okay. So now there are like some small results, some quick to follow results that follows from this equivalence. So like first, every edge of a tree is a cut edge. So let's see over this example first. So if I remove any edge here, right, you can see that, sorry, you can see that it gives you two connected components. So you can just check it for any of the edge. So if I cut this edge, if I cut this edge, you get the same thing. If I cut this edge, you get the same thing. So what it is saying, every edge of a tree is a cut edge. So how will we prove that? So using previous theorem, remember, every edge of a tree is not contained in a cycle. Any edge which is not contained in a cycle is a cut edge. Just see this theorem, the first theorem that we proved. So the first theorem that we proved is what? An edge is a cut edge if and only if it is not contained in a cycle. But tree is acyclic. None of the edges are contained in a cycle. So every edge of a tree is a cut edge. So the first thing is very clear, right? Every edge of a tree is a cut edge. And then the second thing is like if you add any edge to a tree, it forms exactly one cycle. And how the proof will go? So if you take any UV, any two vertices inside the tree, so there exists a unique path in the tree. Like that's the last statement of the equivalence theorems, right? So if you add UV, it exactly creates one cycle. So like let's just see it in an example. So suppose this is U and V, right? And if I add this, it is exactly creating this unique cycle. That's what I'm saying here. Because there already exists a unique path between U and V, which is this. So when you add up UV, you will just form one cycle using that path. Okay. And the last one, every connected graph contains a spanning tree. So how will we do this? So okay, any graph G, we assume that it has n minus 1 edges, because if G has n minus 1 edges, and we also know that G is connected, we know that G is connected. So remember, any connected graph with n minus 1 edges is already a tree. So we don't need anything to prove. That is already a spanning tree. So the second thing that we need to prove is if G has n greater than n minus 1 edges, we can always delete some edges without removing the connectivity. And how will we choose which edges to delete? Basically, if a graph has more than n minus 1 edges, it must contain some cycle. You just go through that equivalence thing and you will see. If it has more than n minus 1 edges and it is connected, it must contain some cycles. You go through these cycles and delete all the edges in this, and delete some of the edges in the cycle. So you delete one by one, and eventually you keep on deleting edges so that eventually you will come to graph with n minus 1 edges, and you end up with a spanning tree. As an example, I'll just draw a small graph here. So suppose this is our graph. So you see there are like many cycles here. So I'll just choose any cycle in random, and so like suppose I choose this cycle. So I just cut this edge. Suppose if I just remove this edge, I've still not removed any of the vertices. All the vertices are there. And we see we again have a cycle. So we just remove a cycle. We just remove this edge. And now we get an spanning tree. So what we have proved is like any connected graph with more than any connected graph actually contains a spanning tree. And how you obtain that spanning tree, you will see a very efficient algorithm in your course. But this is just an existence result that's saying that every connected graph contains a spanning tree. It's an existence of spanning tree inside a graph. Okay, so is this clear? All these three statements, are they clear? So the first statement is every edge of a tree is a cut edge. Second statement is if you have a tree, adding any edge creates exactly one cycle. And the third statement is every connected graph contains a spanning tree. and I've given proof for all of this. Okay. Okay. So now we go to our next theorem, and this is important theorem. So okay, I'll first read the theorem, then I'll give you an intuition of this, and then we'll go with the proof. So this theorem says that if so, remember, first of all, just see, I'm saying that every connected graph contains a spanning tree. So we know that spanning tree exists. Now suppose there are more than one spanning trees of a graph. Let's say that if T and T prime both are spanning trees of the connected graph G. So what it is saying is, like, suppose there exists an edge inside this spanning tree T, which is not in spanning tree of T prime. So it is saying that there must then exist an edge E prime inside T prime, which is not in T, such that when you remove that edge E from T and add edge E prime, you get a spanning tree of G. So just read this statement once again with me. So I'm saying if you have two spanning trees, T and T prime, of a connected graph G, and they are, I'm also assuming they are different because I'm saying there exists an edge which is not in T, which is in T but not in T prime. Then there exists an edge E prime which is not in T but in T prime, such that from T you can construct a new spanning tree of G, which is T. We remove this E, and then add E prime. So let's see this. Let's see the intuition first of this. So we'll just go with our running example. This is our graph G. Let's say we have two spanning trees, T and T prime. These are two distinct spanning trees. Let's say this is edge E. So for this edge E, we can remove this edge E and we can add this edge E prime, and the resulting thing is again a spanning tree. So see, this is the graph. This is one spanning tree, this is another spanning tree. And I am basically telling you how to use the edges of these two spanning trees to come up with a new spanning tree. This is the new spanning tree, T minus E plus E prime. So I'm removing this edge E, and I have an edge E prime inside T prime such that the resulting thing is a spanning tree. So what we are doing, we are kind of replacing edges from two given spanning trees to form a new spanning tree. And this is a very important theorem, and actually generalizations of this statement exist in some deep theories in math, and like you might have heard about it, or maybe you should look into it, like about metroids, and you can just check their definitions. So you will see that this kind of thing actually appears in there, one of the axioms. Check the axioms of, sorry. Okay. So now, if the intuition is clear, then I'll proceed to the proof. So how the proof goes? So we are given two spanning trees, and we are given an edge E. So remember, we know that E is a cut edge from our earlier theorems. We said that every edge of a tree is a cut edge. So that's why I said why, so that to know if you are not sleeping and listening. So every edge of E is a cut edge. We know it from our earlier theorems. So if you remove E, you will have two connected components. Let's say them U and V, capital U and capital V. So uh, suppose this is how they look like. So these are two connected components. So remember, T prime is also a spanning tree. So there must exist an edge E prime connecting some vertex from U to some vertex in V. So that's what I'm saying next. The T prime is also a spanning tree, and so there must exist an edge E prime that connects with some points in U and some points in V. Okay. So, okay, so when we remove this t minus e, we get this disconnected thing. But there already exists some edge connecting these two connected components. So we get a connected graph. And remember, this part is this is acyclic. This is acyclic. And you're not adding any edges on this. You're adding a new edge, which is not in both of these components. So this entire thing is acyclic, unconnected. So then we say t minus e plus e prime is connected. And actually, you can also show by the count of, you can also show the same thing with the argument that it has n minus 1 edges, because you initially had this edge e, or you initially had this edge e, you removed that, you removed this edge e, you remove this edge e, and you added this edge e prime. So the number of edges remains the same, which is n minus 1, and your graph is connected. So it must be a spanning tree. Okay, so are there any doubts or questions regarding this proof for this theorem? So I exactly followed what I showed in the intuition. It's just like I'm proving it for a general graph. In the intuition, I was just going for a specific graph, and I showed you that how I add things and remove things. So what was the intuition? So when you remove this, when you remove this H E, you actually get two connected components. You actually get two connected components. But then T prime is T prime is also a spanning tree. So there must exist an E prime. Sorry. There must exist an E prime. This is the E prime. So then the final thing is again a spanning tree. That was the intuition, and the proof is exactly like that, but for a general graph. I'm not assuming anything for the graph, and that completes the proof. So I essentially use two things. I essentially use the first fact that E is a cut edge, which we showed earlier. And the second thing that we used is that T prime is also a spanning tree. So then we must find an edge E prime. And then the final thing that we use is like it is connected and then edge count argument to show that it is actually a spanning tree. Okay, cool. So similar to this theorem, we have another theorem which looks very similar, but the order of T and T prime are changed here. So if just let me read the theorem first, and then I'll explain what is the difference. So if T and T prime are two spanning trees of a connected graph G, and again we have an edge E from which is in T, which is not in T prime, and then we are saying there exists an edge E prime such that it is in T prime, but not in T. So now I'm saying you can add edge E to T prime, and then you remove E prime, and this is again a spanning tree. What is the difference between the above two? So above, I'm saying you can remove an edge E from T, you can remove an edge E from T, and you can add an edge E prime from T prime, and this forms a spanning tree. Now I'm saying you can add an edge E to T prime and remove edge E prime. It is not exactly reversing the order. There's subtle difference, and you'll see the subtle difference in the proof. So as T prime is a tree, adding any edge will create a unique cycle. Remember one of the other corollaries that I showed? So it will create a unique cycle. So like if as T prime is a spanning tree, we add an edge E from T prime and we get a unique cycle. And then we can always find an edge E prime which is not in T, because T was a tree. So you must find an edge E prime which was not in T but was in T prime. So now, if you remove that E prime, we break the cycle. So you break the cycle and it is connected and it is acyclic. That proves that this is a tree. So earlier we are first deleting an edge and then adding an edge. Now we are adding an edge and then deleting. But where we are adding from which tree to which tree is actually important. So that's the subtle point that you should keep in mind for the proofs of this two theorems. Okay. So are there any questions or doubts regarding this? Okay, if not, then I'll proceed for the next one. So now I will give you some more definitions about the degree and distances. So first, for any graph G, we denote the minimum degree by this small delta G and capital maximum degree with capital delta G. Okay, so we have another interesting theorem, which is this. If T is a tree with k edges, and if G is a simple graph, then with their minimum degree greater than or equals to k, then you should find T as a subgraph of G. Okay, first of all, let me say what is a simple graph, because I've not defined simple graph so far. So simple graph is a graph without loops and multiple edges. Okay, so what is a, okay, so let me add a page here and explain what is not a simple graph and what is a simple graph. Okay, so suppose you have a graph like this. I'm saying these are multiple edges. You have two edges from the same one, two, three. So this is multiple edge. So in a simple graph, this should not be the case. You should not have something like this. And what is a loop? A loop is something like this. You have an edge for a vertex itself. This is a loop. But in a simple graph, I'm not allowing that. So I'm saying I don't have these loops and multiple edges. So this is a simple graph. But this is not a simple graph. This is not a simple graph because I have a loop and I have an edge. Okay. So what it is saying, if any graph, for any graph G, if the minimum degree is greater than or equals to k, then sub you must find a t inside the graph as a subgraph with k edges. So how will we prove? We'll prove it by the induction on k. So base case, when we have k equals to 0, so any graph, um, any vertex in V can be thought of as a tree. Any vertex is actually trivially a tree, which is tree with zero edges. Okay, and now the second thing is, we assume that the claim holds for tree with fewer than k edges. That is our induction hypothesis. So we assume that any graph, if you have this uh, delta G greater than or equals to k, that minimum degree of graph G is greater than or equals to k, then it must contain a tree with fewer than k edges. So let's take it. Now let's say we have now let now say we have k edges. So we choose a V in T, a vertex V, which is a leaf, and let's say U is its neighbor without loss of generality. And then we can remove this V from T, and we'll get T prime. This T prime is actually a tree. Why? Again, just go through the first theorem that I started with. Second theorem actually, where I said that if you remove the leaf, you will again get a tree with fewer edges. Okay, so this has k minus 1 edges, but induction hypothesis says that then the graph G should contain T prime as a subgraph. Now we need to show that using this T prime, that G actually contains T. But how will we go for that? Oh, remember that U is contained in T. And U is also contained in G, but now I'm saying this is a subgraph of G, so it can be labeled as something else. Let's say that it is labeled as X. But we know the degree of X is greater than or equals to K because why? Because del G is greater than or equals to K. So there must exist some y which is not in T prime such that it is an edge in graph G. Why? Because T prime has only k minus 1 edges. But so y, it should have like k edges. So this is y. So it should have k edges. But T prime has k minus 1 edges. So there must be some edge which is not in T prime. So there must exist, oh, sorry, this is x. So there must exist some y which is not in T prime, but is in T. Now we can think of this y as a relabeling of V. Remember, we started with V. So now we can say that this T is a subgraph of G up to just relabeling of certain vertices. That completes the proof. That completes the induction hypothesis, and hence that completes the proof. So see, we did an induction on K. We say that when K is equals to 0, any graph contains a vertex V. And then we say that our induction hypothesis, we claim that it holds for trees with fewer than k edges. Now say we have t with k edges, we choose a leaf, we remove that leaf. Once we remove that leaf, we got a tree with k minus 1 edges. And induction hypothesis say that this contains the subgraph. And using this subgraph, using this fact from T prime, because we have removed V, we just say that, oh, this, because the degree of G is, minimum degree of G is less than k, it should contain some vertex outside this T prime to this U, and then we just extended that argument simply. It's just some relabeling thing, and then we are done. Okay, so are there any doubts, questions, anything? Okay, so I will go with the next section, which is distance in trees and graphs. Okay, so I will just introduce you to some new definitions, and then we'll prove some new cool results about this. So we say a graph G has UV path. If a graph G has UV path, then the distance from U to V is actually written as this D subscript G UV or DUV. When G is clear from the context, you don't write G as a subscript. Is the least length of the UV path, right? You take all the paths connecting U and V, and you choose choose the path with the least length, and that is the distance between U and V. And if no such path, if there's no path connecting U and V, suppose you are taking two vertices from the two different connected components of graph G, then this DUV is actually infinity. This is just a notation that we assume. Okay, so now we define diameter. Diameter is for any, so now you have a notion of distance between two vertices, and diameter is basically for, you just compute the distances for all the vertices in the graph and take the max of that. That is diameter. Eccentricity is for any vertex you find the distances from all the vertices connecting you, all the paths to all the vertices, and take the minimum of that. That is eccentricity. Oh no, take the maximum of that. That is eccentricity. So for any vertex you take the max. So you take all the vertices V inside the graph, you compute the distance and take the max of that. That is eccentricity. And radius is like for all the vertices, you compute eccentricity of all of them and you find the minimum of it. That is the radius of the graph. So are these definitions clear? Okay. So I'll just repeat them once again. So diameter is like you, for any two vertices, you compute the distances and you do it for all the vertices, and the maximum distance is the diameter. For the eccentricity is defined for a vertex. For a vertex U, you choose all the vertices V in the graph and you find the distance, and the max of that distance is eccentricity. And radius, you compute the eccentricity of all the vertices and find the minimum of that eccentricity. That is the radius. Now there are some exercise. So suppose this is the graph. I want you to, so all these numbers are basically eccentricities of these vertices. So I want you to compute the eccentricity of this. And once you've computed the eccentricity of all of that, you see it's very easy to find diameter and radius. So the minimum eccentricity is 2 and the maximum eccentricity is 4. So radius is 2 and diameter is 4. Why? The max of eccentricity is giving you the diameter and the minimum of eccentricity is giving you the radius. And also check the length of the longest path is 7. Okay. Now we come to another exercise, and this is the Peterson graph. This is one of the most important example of graph. So it is used almost every time in graph theory when you have to find a counterexample or when you have to check something. This is really one of the most important graphs that you should keep in mind when you're doing graph theory. So this graph looks something like this. What I want you to do in exercise is like find the radius and diameter and show that this is 2 and 2. Okay, just take it as an exercise. Just go through the definitions, find the eccentricity of all the vertices, and then try to find the radius and diameter. You have to just do explicitly. It is a very good exercise to do. Very fun, and it's also not very difficult. You have to just play around with this graph, and it helps you to get accustomed to this graph. Okay, now I will introduce you to another notion called complement in of a graph. So for a graph, okay, let me first define this. So a complement G prime of a simple graph G, it is denoted by G and then a bar over it, is the simple graph with vertex at V such that UV belongs to the edge of G prime if and only if UV does not belong to the edge of E. Okay. And the next definition is a clique. Clique is in a graph is a set of pairwise adjacent vertices. And an independent set in a graph is a set of pairwise non-adjacent vertices. I will show you them. I will show all of these things in an exam so that the definition becomes clear. Again, I will read the definitions again. A complement of a graph G can be constructed from G. So if you don't have an edge inside G, then you must have an edge inside the complement of it. So just construct the graph G and you construct another graph G prime by adding all the edges which are not in G between all the vertices. You get an E prime, G prime. A clique in a graph is a set of pairwise adjacent vertices. So it's a set in which all the vertices, all the pairwise vertices are adjacent. An independent set is a set in which none of the pairwise vertices are adjacent. So let's see an example. So this is a graph G. This is a graph G, and how will you compute compute the complement? This is the complement. So let's just check the definition. So you don't have an edge UW here in G. So you have an edge UW here. You don't have an edge YV in G. So you have an edge here in the complement. Similarly, you do it for all the things and you get the complement. Okay, in this graph, you might ask what is the clique. So this is a clique. This is one of the cliques. Why it is a clique? So UYX is said to be a 3 clique because the set has size 3, clique of size 3. So UV has an edge, XY has an edge, YX has an edge. So all three pairwise combinations of these vertices have an edge. UV is UW is not a UW is an independent set. Sorry, let me write this properly. So QW is an independent set of size 2. Why it is an independent set? Because there is no adjacency here. You can just do it with other examples and play around with these definitions till you become comfortable with this. Okay, now there is a very nice and short theorem about the diameter. It says if you know that the diameter of the graph that you're working with is greater than or equals to 3, then the diameter of the complement is less than or equals to 3. So how will we prove this? So we just have to unravel the definitions. You just have to go through the definitions. You have to just write the definitions out, and then you'll see how it works. Okay, so first we assume that diameter is G is greater than or equals to 3, which is you can also write You can also write is greater than 2 because this is because it is greater than equals to 3, right? So diameter is G is greater than 2. So that means there exists U, V in G such that for all x belongs to for all vertices in V, either Ux is not an edge in G or Vx is not an edge in G. Why? Because if this is not the case, then diameter is less than equals to 2, right? So for all the vertices in the graph, either Ux is not an edge or Vx is not an edge. Because if you have for all vertices, either if Ux and Vx both are edges, then diameter is less than equals to 2. So this is just opening the definition. And you also have that UV is not an edge. For so like so now using this definition, we have that for all UV. Oh, so this should be okay. I think I'm mistaken with the quantifier. Uh, yeah, it should be for all UV in T. For all the vertices, um, you should have this. UX is not an edge and VX is not an edge. Now, using the definition, we know that UV should be an edge in G prime, and for all X inside this complement, either UX is an edge in G prime or VX is an edge in G prime. Once you have this, you see that this is the largest path that you can have in this graph, which is of size 3. If this is the largest path that you can have in the graph, which is of size 3, that shows the diameter is less than or equals to 3. So what we are saying, for all UV, so this is just opening the definition of diameter. I opened the definition here, and using the definition of complement, I just in place of these things, I just substituted this in complementations. Once I got this, I can see it is very easy to see that this is the path of largest length of path, and that is size 3. So diameter of G prime cannot be more than 3. So that completes the proof. Okay, so just go at home and just try to write it on your own, and then it will be much more clear. Okay, so now we come to the another definition, which is center, which uses the definition of eccentricity. So we define center of a graph as a subgraph induced by the vertices of minimum eccentricity. So let's go to this definition. Okay, so in this graph, the vertex of minimum eccentricity is only 1, so the center is only 1. This is the only center. But if you have like more than one vertex with minimum eccentricity, then the subgraph induced by that is subgraph, yeah, that is subgraph induced by those vertices forms the center. That's what we call center. Okay, now this is again a very easy exercise. I want you to show that a center of a graph is the entire graph if and only if the radius and diameter are equal. So radius is what? So like when all the vertices have minimum eccentricity, and that will give you the center of the graph. So just open the definitions and you'll see it coming through. Now we'll come to the final theorem of this lecture, which is center. I'll show that center of a tree is a vertex or an edge. So for all the trees, any tree, center of an edge is either a vertex or an edge. Okay, so we again proceed by induction on the number of vertices. So a number of vertices n. So the base case of this induction is when n is less than or equals to 2. So we just show that when n is equals to 1, the center is just one vertex because there is just one vertex and no edges in the tree. So that is the center. When n equals to 2, you only have a path, that is the tree. So the center is just both of these. So these are the eccentricities of these two vertices. So this is the center. Now we assume that this claim is true for n less than k. Whenever the number of vertices is less than k, the center of the tree is either a vertex or an edge. That is our assumption. Now, suppose we have a tree with what k vertices. Now we have to show that the center of this tree T is either a one vertex or an edge. That's what we want to show now. So now let T prime be the tree obtained by removing all the leaves of the tree. So when I'm saying removing all the leaves, I just need to draw something so that you have an intuition. So suppose this is the tree T. So I'm saying remove all the leaves. What I'm doing, I'm removing all these things. I'm getting to something like this. This is T prime. This is the intuition. So now I'm saying obtain T prime by removing all these things, and you'll still get a tree. Why you will get a tree? Just use the first theorem that I showed of trees, that removing a leaf will always give you a tree. If you do it for all the leaves, you will again get a tree. Just take it as an exercise that it is still a tree. So T prime is still a tree. But T prime is a tree with less than k vertices. So now T prime must have center as its. So T prime must have either one vertex or an edge in its center. That is our induction hypothesis. So center of T prime is either a vertex or an edge. These are the two cases. So this is what the induction hypothesis says. This is the induction hypothesis. Now, to complete the proof, if we show that T contains the center of T and T prime is same, then we are done, right? Because center of T prime, we know that it is a vertex or an edge. But if we show somehow that the center of T is same as center of T prime, then we are done. That will cover the proof. So that is what we are going to do now next. So yeah, but now I will leave some of the things for you as an exercise, because these are again very easy to unravel definitions, just so that you get a practice with these definitions, and that's how you'll develop the intuition for this new definitions that I introduced today. So I'm saying for this T prime, eccentricity of T prime in U, for all the vertices U in T prime, eccentricity of that is nothing but eccentricity of U in T minus 1. So like, okay, let me show it with this example. So, okay, suppose this is U. Suppose this is U. And this is the same U. So I'm saying E of U. So you get one eccentricity here, right? And then you get one eccentricity here in the big tree. And I'm saying E of T prime U is equals to E. The eccentricity of U in T prime is nothing but eccentricity of U in T minus 1. Just open the definitions and we'll see that. And the second thing that I want you to show is that eccentricity of leaves is always greater than their neighbor. So like, okay, let me add a page and just draw something so that you get an intuition for what I'm saying. So suppose this is the tree. So suppose this is V, suppose this is U. U is a leaf, and I'm asking you to prove that I'm saying that ET of U is always greater than ET of V. So eccentricity of the leaf is always greater than the eccentricity of their neighbor. Once you show once you show both of these exercises, you essentially show that the set of vertices minimizing the eccentricity are same. Because suppose this is the tree that we started. So this is the original tree that we started with. And these are all the leaves that we are removing to obtain T prime. And now I'm saying in T prime, the eccentricity of T, so all these vertices, the minimum eccentricity of the vertices remains same, because I'm saying you just add 1 and you get for all the vertices, you just add 1 to this. So the vertices for which we achieve the minimum eccentricity is same inside this set. And the second exercise that I'm asking is that eccentricity of the leaf is always greater than the neighbor. So all these vertices will not contribute to the set of vertices which are giving you the center. So the center of T prime gives you the center of T. So that's what I'm saying. The center of T is either, and once we know the center of T prime is either a vertex or an edge, because from the induction hypothesis, that completes the proof. I'll just go through it again. So first we want to prove the center of a tree is a vertex or an edge, and we proceed by the induction of the number of vertices. So now there are two things. Uh, the base case is endless. We have to show that base case. For base case, we showed n equals to 1 and n equals to 2. And the induction hypothesis, we assume that the claim is true for any vertices less than k. And from the tree T with k vertices, we removed all the leaves to obtain T prime. And because T prime has less than k vertices, we can use the induction hypothesis to say that the center of T prime is either a vertex or an edge. Once we know that, and then I gave you two exercises that the eccentricity of vertex u in T prime is nothing but eccentricity of u in T minus 1, and the eccentricity of leaves is always greater than their neighbor. So that is essentially like saying that that these two exercises shows that the set of vertices which minimizes the eccentricity are same. In other words, the center of T prime is same as center of T. And we already know the center of T prime is a vertex or an edge. That completes the proof. Okay, I will end this lecture with this last exercise. This is just again just open the definition on your it's easy to see. So if H is a subgraph of G, then the distance of UV in G is less than distance of UV in H. So why this is the case? Let's see it over an example. So suppose this is G and this is H. So let's say you have A, B, C, D, you have A, B, C, D. So distance between B and D in G is actually 1 because you have an edge. But distance between B and D in H is actually 2 because you have to go through here or here. You can just directly do this. So if for any H, any subgraph of G, distance between U and V in G is actually less than equals to distance between U and V of H. So that is the last theorem, last exercise that I give you. Okay, so I will stop the recording now.